Okay, let's look at linear homogeneous equations with constant coefficients. And of course, this is second order differential equations we're looking at. And a significant type of them is of the form x double prime plus p times x prime plus q times x equals 0. And to shorten this down, basically, you can write it as a characteristic equation, which is lambda squared plus p times lambda plus q equals 0. Basically, lambda is lambda is basically raised to the power of the derivative of the x value in here, if you will, or whatever the unknown term is, unknown variable solving for. So x is raised as far as derivatives are. This is the original saying that's the first derivative. We have the second derivative, the first derivative, and the original variable. You could say it's the zeroth derivative, the original thing, sort of. So that's why it's like lambda raised to the 0 power here is sort of what's going on, so it's not shown, but you have lambda and lambda squared, you can think of it as, because second derivative and first derivative is lambda squared and lambda respectively. But yeah, you can write it as a characteristic equation here and solve for lambda. And that determines your solutions, basically, is what your lambda values are. You'll get two of them since we're solving a quadratic equation. But yeah, what we get basically, using lambda values, we get a fundamental set of solutions, is one way of calling it, or FSS. And you use that to form your solution to your equation, to your differential equation. But yeah, basically you have 3 different cases, and it's based on p squared minus 4q. That's what you can say equals that. And if it's greater than 0, it means that lambda 1 does not equal lambda 2 and they are real numbers. You can just solve it and see it for yourself. It's not worth learning the theory behind it. All you have to do is remember this part is so if you have 2 unequal but real lambdas, then you get e to the lambda 1t, e to the lambda 2t as your fundamental set of solutions. Case 2 is where you have delta equals p squared minus 4q, which is equal to 0. Oh yeah, and this comes from the quadratic formula. This is basically what's underneath the square root. If you always use this exact form for solving it, you have it in this form, you always get p squared minus 4q as underneath the square root taken when you solve for the quadratic formula. The quadratic formula has a big portion of it be under the square root, and you'll see that pretty shortly. But it could be written as p squared minus 4q. I prefer just to solve it anyway, not worry about that too much. But to each someone's own. Yeah, so when you have this, though, you have basically the first case is when lambda 1 does not equal lambda 2 and they're real numbers. Second case is when they are real numbers, and they're equal to each other. So we have lambda 1 equal lambda 2. So we have to... And part of this theory is based on linear independence, like in the last section a little bit we talked about. So as a consequence of needing these to be sort of linear independent, we have e lambda 1t be one of the solution, and t times e to the lambda 1t. They're both lambda 1t, because lambda 1 equals lambda 2t. It's just that we add t in here. That's the main difference between this and that, is that you have the second one be different with t, since they're both raised to the same power. And case 3 is when you have complex numbers, your roots, your lambdas are going to be, because the square root of a negative number means you have a complex number. And like any complex number, it's written as a plus ib or a minus ib, basically, and that's what they are. The roots will be plus or minus I times b, basically, will be part of it. So you have plus ib and minus ib. I is your imaginary number, of course, and a and b are real numbers. But yeah, the form of this becomes e to the at times cosine of bt, and e to the at times sine of bt. These are two of your two solutions. And like in the last section, you might have seen all these similar forms being used for some of the given solutions, and that's why, because a very common type of problem is this where this type of form is seen in multiple sections at times. In the next section will also cover this type of form where you have it equal to 0. Yeah, that's why we can easily solve for use the quadratic formula to solve our quadratic equation. And that's what the bulk of all this is solving this. Lambda squared plus p times lambda plus q equals 0. And with that explanation out of the way, let's go on. So we find a general solution to each differential equation in pretty much every problem except for the last couple. Last few. So y the second derivative of y minus y prime minus 2y equals 0. So lambda squared minus lambda minus 2 equals 0. And some of these you can quickly, you can just factor, FOIL, whatever you want. Basically you reverse FOIL, so you form it into lambda minus 2 and lambda plus 1 here. Because if you were to, as they say, FOIL, you multiply these together, you'll get lambda squared minus lambda minus 2 equals 0. And as per basic algebra theory, lambda 1 equals negative 1, because lambda plus 1 equals 0 implies lambda equals negative 1 here. And lambda minus 2 equals 0 means lambda equals 2 is another solution. So the real and the not equal, so a fundamental set of solutions is just e to the 2t and e to the negative t. And the solution is y at t equals c1 times e to the 2t plus c2 times e to the negative t. And c1 and c2 are distinct constants. And we can't solve them without initial conditions. So that's all. But it's then it continues on with more examples. So y double prime plus 5y prime plus 6y equals 0. We have our characteristic equation in purple and solving for it. This one can also be split up, so lambda plus 3 times lambda plus 2. And we eventually get e to the negative 3t, e to the negative 2t as a fundamental set of solutions. And you plug that in, you make y at t equals c1 times e to the negative 3t plus c2 times e to the negative 2t. And that's the format. It's always the two constants. It's the summation of the fundamental set of solutions with the constants involved, like in this format for each of them. That's where your general solution will be. 2y double prime minus y equals 0. So we divide by 2 to get, because you want y double prime or whatever it is that's taking the second derivative of by itself. So we divide everything by 2, then we form the characteristic equation. And you could always use the quadratic formula, which is lambda 1 and lambda 2 equals, basically, when you see that below here, but basically it's like your lambda equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And that's going to be shown basically without the symbols being just quickly plugged in. That's all it is. But yeah, you can technically split this up, but if you can't, you can always solve it that way, and you'll still get these somewhat clean numbers. But no, this equation can be split up into lambda minus 1 and lambda plus 1/2, the product of these two binomials. And you get lambda 1 equal 1 and lambda 2 equal negative 1/2. So these are real numbers, different real numbers, so again the same format. c1 times e to the t plus c2 times e to the negative 1/2. And now for this one here, you could probably split it up, but it's easier just to sometimes do it by lambda, so I want to show it. Yeah, but first, you have to divide by 3 to get y double prime minus 2/3, y prime minus 1/3, y equals 0. You always do that. Get in the format where this is, Then we have lambda squared minus 2/3 lambda minus 1/3 equals 0. And we set up the quadratic formula. As you can see, as I said, negative b. And we have b squared minus 4ac, all divided by 2 times a. In these problems, though, a is always going to be 1. So just a quick note. This is b is p, of course. Like if you look back on this real quick, just not to get too distracted, but I think these are a little too simple, these ones. So it's p squared minus 4q, and p is b. Q is c. So yeah, same format basically, because your a term traditionally can be thought of as just 1 always. So, yep. You have p squared minus 4 times q, basically. And this one's going to be greater than 0. So, of course, we're going to get 2 real solutions. But I think it's better just to solve them as they are instead of worrying about all that stuff. And just understand what to do when you get your answer. Yeah, you go through the process and you get your lambda 1, lambda 2 equal to 2/3 plus or minus 4/3 divided by 2, and then you separate them into plus and minus ones. And we get 1 and negative 1/3. So e to the t power and e to the negative 1/3 t power are a fundamental set of solutions. So y at t equals c1 times e to the t plus c2 times e to the negative 1/3 t power. And that's it for that. No, it's time for another one. And these are kind of ordered, so there's 4 of each type, basically. That's how I just sort of fit them in. That's how the book organizes them and everything. So here we have y double prime plus y equals 0, which looks innocent enough. It looks very simple. So this is lambda squared plus 1 equals 0. And then you subtract by 1 on both sides to get lambda squared by itself, because we can solve this right away. But it's lambda squared equals negative 1. So lambda 1 and lambda 2 are equal to the square root of negative 1. So lambda 1 equals 0. I put 0 here just to keep remembering it. Plus I times 1. Lambda 2 equals 0 minus I times 1. We do this because it's in the format of a plus I times b and a minus 1i times b. They're complex and they're not equal to each other, so of course the complex is always going to be like that. That's how it works in each of them, in these types of problems. So it's e to the 0 because it's e to the at, so a is 0, so it's just e to the 0 for them. And it's cosine times b. It's cosine and sine of b times t. B is 1. So this is like one of the most simple fundamental set of solutions. It's literally just cosine of t and sine t. So it's c1 times cosine t plus c2 times sine t, and that's a very good start to this type. We're going to have 3 more of these right now in a row. And we're going to use the quadratic formula in many cases. This one. So we have just direct translation into it. It's lambda squared plus 4 lambda plus 5 equals 0. You solve it with the quadratic formula, and you can, of course, simplify down until you're ready to do the split. This time, I have negative 4 plus or minus 2i divided by 2. So you can divide both by 2, so we do it anyway just to get it down. So just negative 2 plus or minus I. So negative 2 plus I times 1 and negative 2 minus I times 1 are lambda values. Oops. So it's e to the negative 2t times cosine of t because it's b is equal to 1 and a is equal to negative 2. And e to negative 2t times sine of t. And then you just do c1 times e to the negative 2t times cosine t plus c2 times e to the negative 2t times sine t for our actual solution, the general solution to this problem. And again, with more examples of this. Y double prime plus 2y equals 0 means lambda squared plus 2 equals 0, so lambda squared equals negative 2. Take the square root. We have square root of a negative number, so this is equal to square root of the square root of negative 2 is the square root of 2 times the square root of basically negative 1 is how you can theoretically think of it. And the square root of negative 1 is I. That's how it's defined. So that's why it's split up like that. So we have 0 plus square root of 2 times I and 0 minus square root of 2 times I. So we have C1 times cosine square root of 2t plus C2 times sine square root of 2t. Square root of 2 times t, that is. Just the square root of 2 times separately t. Basically. Just to make sure you understand that. But nope, square root of 2 is what's in matter. Yeah, your a and b term matter here. Yeah, that's why I always put the 0 there if any of the terms are like that. And we have y double prime minus 2y prime plus 4y equals 0. So lambda squared minus 2 lambda plus 4 equals 0. Set up the quadratic formula. We eventually get 1 plus or minus square root of 3i. Yep, and then e to the t, because a is 1, b is square root of 3. So you get basically an end y at t equals c1 times e to the t times cosine square root of 3 times t plus c2 e to the t times sine square root of 3t. As shown. And now we're going to look at the other case where the roots are equal to each other. Our two lambda values are equal to each other for the next several. Then we have some initial value problems of that. But first, in this case, it's lambda squared minus 4 lambda plus 4 equals 0. And we can split it up into two binomials, the product of two. So it's like lambda minus 2 times lambda minus 2 equals 0. Yep, when you figure it out quickly, 4 divided by 2 is 2, and lambda minus 2 times lambda minus 2 will be equal to this quadratic equation. So lambda minus 2 squared, I emphasize that here, then it's equal, so lambda 1 equals 2 is equal to lambda 2. Trying to emphasize the point here. So we have e to the 2t, and t times e to the 2t is our fundamental set of solutions. So y at t equals c1 times e to the 2t plus c2 times t times e to the 2t. Yeah, and then we have 4y double prime plus 4y prime plus plus y equals 0. So we divide everything by 4 first to get y double prime plus y prime plus 1/4 y equals 0. And then we can set it up as a characteristic equation and then solve that for lambda. Yeah, we could have probably solved this just like this one here, but hey, it doesn't hurt to do it this way sometimes if you're not sure, if you can't come up with it. Especially when fractions are involved or decimal points, you really don't want to do this. You'd rather do it this way, just spend a little bit more time on it to make sure you do it right. But as you can see, we get right here, we have b squared minus 4q. We have p squared minus 4q. So it's 1 minus 1, and that's 0. So again, delta equals 0 here. As it said at the beginning, just that's the one time I like to show it, just something to occasionally note. That's what happens. So we get negative 1 plus or minus 0 divided by 2, so it's negative 1/2 and negative 1/2. So same value, so it's e to negative 1/2 t, and t times e to negative 1/2 t. So fundamental set of solutions, so y t equals c1 times e to the negative 1/2 t plus c2 times t times e to the negative 1/2 t. Then we have two more like this where it's figuring them out. So here, 16y double prime plus 8y prime plus y equals 0. Divide by 16, and then we make the characteristic equation from that. We solve this, and we eventually get negative 1/4. The value of both lambda 1 and lambda 2, so e to negative 1/4 t, and t times e to negative 1/4 t, and then you have the solution like before. Same format. So in 23, it's 16y double prime plus 24y prime plus 9y equals 0. We divide by 16 and simplify and get a characteristic equation from that. Lambda squared plus 3/2 lambda plus 9/16 equals 0. We take the quadratic formula and solve for lambda and get negative 3/4. So lambda 1 equals negative 3/4, which is also equal to lambda 2. Then we have e to the negative 3/4 t times e to the negative 3/4 t as a fundamental solution. So y at t equals c1 times e to the negative 3/4 t plus c2 times t times e to the negative 3/4 t. And now let's look at 4 initial value problems just to get the juices going still. Since these are pretty cool problems and quick to solve. No, so I'm not going to do all these, but I'm just saying like this the only other thing really left to do is solving initial value problems. Since as of right now we're not worried about word problems or any type of condition stuff. You have to think about how to set it up. So y double prime minus y prime minus 2y equals 0. This means lambda squared minus lambda minus 2 equals 0 is the characteristic equation. We can split that up into lambda plus 1 times lambda minus 2 equals 0. And we have lambda 1 equals negative 1, lambda 2 equals 2. So e to negative t and e to the 2t are fundamental set of solutions. And y at t equals c1 times e to the negative t plus c2 times e to the 2t. So that's our general solution. Okay, very quickly. And we are given, I wrote this a little bit later, just this time especially. So we're given y of 0 equals negative 1 and y prime of 0 equals 2 in the problem. And we have to solve basically, you have to solve for your constants, and that's all, like before. This time though, we have y of 0, we have y and y prime, so we'll just solve these individually to show. It is a better visualization that makes it a little bit more interesting in another problem. So we have y of 0 equals negative 1, which is equal to c1 times e to the 0 plus c2 times e to the 0. So this means c1 plus c2 equals negative 1 because e to the 0 power is 1. So just c1 plus c2. So c1 equals negative 1 minus c2, though we can solve for c1. So we need the other thing to solve for. So y prime at t, we have to take the derivative of what we found to be y at t. And then we use the initial condition for that. So it's just, you drop down negative 1 from here, so it's because that's derivative of negative t is negative 1. So negative c1 times e to negative t plus 2 times c2 times e to the 2t. Because we drop down to 2 for that. So y prime of 0 equals 2 is equal to negative c1 times e to the 0 plus 2 times c2 times e to the 0. This means 2 is equal to negative c1 plus 2c2. We solve for c2 to get c2 equals 1 plus c1 divided by 2. Then we plug in a value of c1 for this. Or we can plug in, we basically plug 2 into 1 here. So 2 into 1. We get c1 equals negative 1 minus 1 plus c1 over 2. So it's c1 equals negative 1 minus 1, because we just do negative, minus c1 over 2. So this means we have 2c1 over 2 because we added c1 halves, basically. So c1 plus c1 divided by 2 is, I see what I did. So 2 times c1 over 2 plus c1 over 2 because I multiplied by top and bottom by 2, which you can do. Visualize when you add them. And that's all equal to negative 2 because negative 1 minus 1 is negative 2. So we have 3c1 divided by 2 equals negative 2. 3c1 equals negative 4, and then c1 equals negative 4 thirds, so algebra. And then that means c2 is equal to 1 plus c1 over 2, so that means that c2 is equal to 1 plus negative 4 thirds divided by 2, which is equal to 1 third when you do the math. So y at t equals negative 4 thirds times e to the negative t power plus 1 third times e to the 2t power. That's how you solve that type problem. We have a few more initial value problems, and that's it for this section. So here we have y double prime plus 25y equals 0, y 0 equals 1, and y prime of 0 equals negative 1. So lambda squared plus 25 equals 0, lambda squared equals negative 25, so we have complex numbers in here, so because it's the square root of negative 25 we need. Same process before. C1 times cosine 5t plus C2 times sine 5t is what our solution is. And of course, we do y prime of t equals negative 5 because with sine and cosine, the derivative of cosine of something is sine, negative sine I mean. time, and if the derivative of 5t is just 5, so it's negative 5 times c1 times sine 5t plus derivative of sine of something is just positive cosine times the derivative of the inside. So it's plus 5 times c2 plus 5 times c2 times cosine of 5t. And cosine of 0 equals 1 and sine of 0 equals 0, so this will be very quick to do because of that. You can only say them as. And we find that's actually very quick to solve. And I set it up like this with them both next to each other so you can solve them. Y of 0 equals 1 and y prime of 0 equals negative 1. And we plug in the values of 0 for all of them. And we just get c1 plus 0 and 0 plus 5 times c2 from the right hand side. So c1 equals 1, 5c2 equals negative 1, and then divide by 5 to get c2 equals negative 1/5, c1 equals 1. So y at t equals cosine 5t minus 1/5 times sine of 5t. And that's that. So in this one, it's y double prime plus 10y prime plus 25. Y equals 0. Y of 0 equals 2. Y prime of 0 equals negative 1. So lambda squared plus 10 lambda plus 25 equals 0 is a characteristic equation. We can split this up into lambda plus 5 times lambda plus 5 equals 0. So we have lambda 1 equals negative 5 equal to lambda 2. Again, set of solutions. So we have y at t equals c1 times e to negative 5t plus c2 times t times e to negative 5t. Our general solution right here. So now we have to solve for c1 and c2 to get our specific solution to this IVP. So we take the derivative of this, again, negative 5 because it's dropped down, and seeing as that, so we have that to left, okay. Then we have the product rule, because t is a function and e to negative 5t is a function, so basically they're not constant. So c2 is constant, so it's multiplied against whatever it is. So first I took the derivative of e to negative 5t for the first one, and t stays constant for that in this one. So negative 5 times c2 times t times e to negative 5t, okay. Then we add c2 times e to negative 5t just alone. Because the derivative of t is 1, so 1 times e to negative 5t times c2. Yep. Then y of 0 equals 2 equals c1 times e to 0 plus c2 times 0 times e to 0. Y prime of 0 equals negative 1 is equal to 5 times c1 times e to 0 minus 5 times c2 times 0 times e to 0 plus c2 times e to 0. E to 0 power is just 1. It's going to cancel out a lot of stuff solely. So we have 2 equal to c1 plus 0. And negative 1 equals negative 5 times c1 minus 0 plus c2. So c1 equals 2. And negative 1 equals negative 5 times 2, which is c1's value, plus c2. So we have eventually negative 1 equals negative 10 plus c2. And then finally, c2 equals 9 because negative 1 plus 10 is 9, so c2 equals 9. So y of t equals 2 times e to the negative 5t plus 9 times t times e to the negative 5t. And finally, a slightly more harder one. Y double prime plus 2 times y prime plus 3y equals 0, y of 0 equals 1, y prime of 0 equals 0. So lambda squared plus 2 lambda plus 3 equals 0 is a characteristic equation. And let's solve this using the quadratic formula. Eventually it simplifies down to just negative 1 plus minus square root of 2 times I. So, yep, and then we get to using our a term is negative 1, our b term is square root of 2. We plug that into our basic formula as we've seen before, and then you just have to remember your 3 conditions, what you get. Especially the last one for the complex ones is very different than other ones. but you get used to it. So y at t equals c1 times e to negative t times cosine of square root of 2 times t plus c2 times e to negative t times sine of square root of 2 times t is our general solution. Derivative of this is messy because we have cosine, we have our trig functions, and we have e to the negative t power. So we have exponential function as well. And the product of them. So product rule is going to be used 2 times, here and here. So I just keep c1 out and then multiply by brackets. We have the first part, so we take e to negative t's derivative is just negative 1. So negative e to negative t times cosine square root of 2 times t plus, minus, because the derivative of cosine is negative sine, so it's, and of course square root of 2 comes out. So it's negative square root, so it's minus square root of 2 times e to negative t times sine of square root of 2 times t. So that's the first part. So then we add c2, so c2 plus c2 times the derivatives here. Again, negative e to the negative t power times sine of square root of 2t, like before, just with sine instead of cosine. Derivative of sine of something is just positive cosine. So it's plus square root of 2 times e to the negative t times cosine square root of 2t. And that's our derivative. So y of 0 equals 1. A lot of things cancel out, so it becomes just 1 equals c1 plus 0. Because remember, cosine of 0 is 1, sine of 0 is 1. And e to the 0 power is 1. So c1 equals 1. Y prime of 0 equals 0. Is equal to all this stuff we plug in. We get a lot of 1s and 0s from it. So we get 0 equals c1 times negative 1 minus 0. Negative 1 minus 0 plus c2 times 0 plus square root of 2. This means 0 is equal to negative c1, because we multiplied it together, plus square root of 2 times c2. So square root of 2 c2 equals c1, basically, because you add c1 to both sides. Then we get c2 equals c1 divided by square root of 2. Plug in c1 equals 1 to it, so it's c2 equals 1 divided by square root of 2. Then we multiply by square root of 2 over square root of 2 to make it so we rationalize the fraction, so it has the radical on top of the square root. So it's square root of 2 over 2 is, square root of 2 over 2 is identical to 1 over square root of 2, except for just where the radical is. But it means the same, it has the same exact sign if you plug both into the calculator. So finally, y at t equals e to the negative t power times cosine square root of 2 times t. And then plus square root of 2 divided by 2 times e to the negative t times sine square root of 2 times t. And that's the final solution to this IVP in the final thing. And that's it for this lesson, but it's not that hard to solve and everything. You just have to remember your cases correctly. The two real cases are very similar. You just have to remember that you add something special in. You multiply by t to one of them. Just remember that. And when they're different, it's e to the lambda 1t and e to the lambda 2t, so the different lambda values. Here the lambda values are the same, so it's e to the lambda t basically, and t times e to the lambda t basically. Then the complex is its own thing. But that's the best I can offer for this. And practice is the only other thing that can make you remember it.